Let's continue with question 3 on the 2023 AP exam. So this question is a little complicated, so I've already set up the equation and I'll explain what I'm doing in a minute. But basically the question states that the HCl aqueous was excess in this reaction, so I rewrote the reaction. And we need to determine the molarity of HCl. So remember, molarity is another word for concentration. So I need C equals N over V eventually to get the answer. But I need to find the molarity after the reaction is complete in trial 2. So when you do your answer, the HCl's molarity or the HCl's concentration, this will represent the excess. The excess HCl you have after you've completed this reaction. So I like to set this up using a BCA table, which stands for before, change, and after. And before, what that means is if you go all the way back, you have to look at the data table from this question. So it says to use trial 2. So before we started or before we mix these things together, I have a concentration of HCl of 1.00 moles per liter, and it's reacting in a volume, or it's occurring in a volume of 50 milliliters. So what that means is if I use my mole equation, N equals C times V, I'm going to do it up here because I don't have a lot of space underneath. N equals 1. Actually, you know what? I should probably do this by the question because I think that's how it gets marked. So I'm going to do it here. So the moles equals 1 mole per liter times a volume of 0.0500 liters. Remember to change the milliliters to liters so that the unit cancels out properly. And I have a mole value of before of the HCl, 0.05 moles. Now, okay, and I know this is excess. And by the way, I can also change the calcium carbonate into moles. So N equals M over M, because if we go back to the question up here, I am using 1 gram of calcium carbonate in this reaction with my HCl. Okay, so let's go back here. N equals, I'm going to just try to put this here. So 1.00 grams divided by the molar mass is here, 100.09 grams per mole. So I have a moles of CaCO3. By the way, the calcium carbonate is my limiting reactant. 0.00999 moles. So I know that when it comes to the change, because the calcium carbonate is my limiting reactant, all of it reacts. So after the reaction, I have a mole value of 0 moles of calcium carbonate. It's my limiting, so it gets fully consumed. All right, now I want to figure out how much did the HCl change by. So this is what I have initially. How much of the HCl did I actually use? So to figure that out, I need to do a mole ratio, which I'm going to do on the side. What I'm going to say here is that for the HCl, I know that I reacted 0.00999 moles of calcium carbonate. So I'm going to multiply this by a ratio to cancel out CaCO3, so that will go on the denominator, and then the moles of HCl will go on the numerator. That's what I want to figure out. And I know that for every 2 moles of HCl used, that's my balanced equation, 1 mole of CaCO3 is used, that's also from my balanced equation. So the moles that are actually used of HCl are 0.0200 moles. This is actually used, okay? So this is what is reacting. So under the word change, I know that the HCl changes by double the calcium carbonate. So this will decrease by 0.0200 moles. That will leave me with an excess of 0.0300 moles of HCl excess. Now, this is what the question is asking me. So it says here, what is the molarity of HCl in the beaker after the reaction is complete? That's what I'm representing by this in my before change after table. So I'm just going to change concentration, I'm going to change moles into concentration using C equals N over V. And again, if you read the question, all of this is happening in a 50 milliliter beaker, so my volume is the same. So C equals 0.0300 moles divided by 0.05 liters. My concentration is we're going to round it to 3 sig digs because that's how many I'm given in the question. So very long kind of solution. You can do it different ways, but I like to set up the chart to help me organize my thinking. This concentration of HCl is my excess amount after we mixed 1 gram of CaCO3 with 1 moles per liter of HCl. 1 moles per liter and 50 milliliters of HCl. So when you mix these together, you're left with an excess amount of 0.600 moles per liter. I hope that makes sense. Please put a question in the comments if you don't understand, okay, or if you need a additional explanation. Continuing on in this question, I'm given a data table. So same experiment. Okay, I'm mixing the 50 milliliters of HCl with 1 gram of CaCO3 in a calorimeter, but this time I'm recording the temperature change. And so if I visualize it like this, I have a beaker or a calorimeter here. This is HCl. There's 50 milliliters of it. Now HCl is aqueous, right? So most of this is actually water. And then I'm putting in here 1 gram of calcium. We'll call this CaCO3. And when you mix these things together, you're going to measure the temperature change. And what I've seen is that the temperature started at 21.2 and it rose to 21.9. So the temperature went up by positive 0.70 degrees Celsius. So actually the water is getting hotter. So as this thing dissolves, what's happening is the water is getting hotter. I'll put arrows like this. Now the water is my surroundings. So if my surroundings are getting hotter, this is an exothermic reaction. So justify using the data table, I can justify this by saying that the water, which is the aqueous part of HCl, got warmer by 0.70 degrees Celsius. And because the water is the surroundings, the water is the surroundings, and we know that in an exothermic reaction, that's the definition, heat goes from the system to the surroundings. So the water is the surroundings, and the surroundings warmed up, and which is consistent with exothermic. I don't know why that keeps erasing there. Exothermic reactions. You can word this better. You can look at the answer key online and try to word it a bit nicer, but hopefully that gives you the idea. Moving on, let's see if I can finish solving this in one video. So based on the experimental data, the mass of the system is 51 grams and the specific heat of the reaction is 4.0 joules per gram degree Celsius. Calculate the magnitude of heat transfer, Q, in joules. So what they want me to do in this question is find Q of the surroundings, and because that's the heat transfer, so it's transferring into the surroundings, that equals MC delta T. You have to be careful with your mass here because it says this is the mass of the system. I want the mass of the surroundings. So if you go back up to my diagram that I drew up here, the surroundings is represented by this part, the HCl. Okay, let me rewrite that here because HCl, the aqueous part, this part is your surroundings. And what I know is that the HCl was dissolved in 50 milliliters of water, which is equivalent to 50 grams. So just be careful. I think the answer key made a typo because the mass here should be 50 grams to represent the mass of the surroundings. We're going to multiply this by 4 joules per gram degree Celsius, and then delta T is TF minus TI, so final minus initial. So it's 21.9 minus 21.2, which is 0.7 positive. I'll just put it like this, 21.9 minus 21.2 degrees Celsius. Put the units, grams cancels out with gram, degrees Celsius cancels out with degrees Celsius. My answer will be in joules, and I will get a positive 140 joules. So this means 140 joules transferred to the water. So the water, surrounding our water, got warmer, and the system, which is the reaction, got cooler. It lost energy. And knowing that is going to help me solve the last one, which is the enthalpy of reaction. So I already wrote down the formula I need. Enthalpy of reaction is delta H Rxn, and that equals Q of reaction divided by what this is the moles of the limiting reactant. So let's do some work on the side. How do I find Qrxn? Well, that's not too difficult because I already solved Q surrounding up there. So I know that Qrxn equals negative Q of the surroundings because if the surrounding gained energy, again, that's what I wrote here, right? If the surrounding gained energy, the system loses energy. So in this, the Q of reaction equals negative 140 kilojoules, it's in joules. But we have to convert it to kilojoules because, look here, our answer needs to be in kilojoules per mole. That's the standard unit. So you move the decimal 3 this way to the left. So Q of reaction is negative 0.14 kilojoules. Now I need to know the moles of the limiting reactant. The limiting reactant was the calcium carbonate. That was 1 gram divided by 100.09 grams per mole. Okay, if you forget, I'm going to scroll up. The answer... these are all related, right? These questions. So you have to, if you get stuck, go back in the questions. There's usually a hint. Sorry, this is messy. So let's get rid of some of this. Where does it say? Okay, sorry. It's even further back. The 1 gram of the calcium carbonate, it's all the way up here. Okay, so it's this value there. 1 gram of CaCO3. And that's my limiting reactant because, again, it told me in the previous question that the acid, the HCl, is excess. So the moles of the limiting reactant is 0.00999 moles of CaCO3. So now we can plug these values into our enthalpy equation, and this will solve our enthalpy. Now notice the sign is important and negative. It says include the algebraic sign in your answer. So delta H reaction will equal negative 14 kilojoules per mole. So that's important. The negative sign also means it's exothermic. Okay, so remember from your class lessons that negative delta H, when delta H is negative, this means exothermic. So that means heat is released from the system to surrounding. And when delta H is positive, that means it's endothermic, endo. And that means heat is absorbed by system from the surroundings. Okay, hopefully you get the idea there. It's kind of messy, but you kind of get what I'm saying. All right, this concludes this question. Yes, it does conclude the question. I hope this helps, and you can watch the next video for the next solution. Thanks.